we have added features to create sensors from templates. This is very useful for a number of reasons. One, it allows you to very quickly create sensor elements that bring in the calibration expressions without having to key in those complicated expressions manually. It also ensures that the calibration expressions are structured in such a way so that you can use some of the additional features we're going to address in a few moments, specifically delta T and its relationship to wavelength ranging. We are going to show that there is several shortcuts for entering in some of the coefficients for temperature sensors. We want to introduce you to some of the color cues that are built into nLight that help you to visually associate different elements, be they FPGs, sensors, and channels together. In other words, be able to see quickly on what channel are the FPGs that are components of this particular optical sensor. We want to introduce you to the concept of delta T and its importance in establishing a measurement system. Specifically, the relationship between the measurement range, such as the strain range, the wavelength range assigned to a particular FPG, and the operating temperature range that the sensor is going to be exposed to. We'll also talk a little bit about sensor calculation shorthand expression. So let's go through some examples, and then we'll come back to this list and make sure we've covered our points. So back to nLight, and we have gone through our acquisition tab to establish our spectral peaks, and we have created FPG elements, and we have informed nLight of the distance between our interrogator and those FPG elements to make sure that we get the best wavelength measurements possible. So now that we have FPG elements, those are really our variables that we can use to create sensor expressions. So let's go, let's see, we are presently on slide 10. I'm going to jump back down to slide 3. We're going to look at our structure. So we have connected 2 fibers to our interrogator, and on the first we have an OS3600, an OS4100, and an OS3100. Now, unfortunately, in my diagram, I don't think I put those in the right order. So we're going to override our diagram a little bit here as we establish the order of those sensors. But we do know that we want to create an OS3600 element and an OS3100 and an OS4100 element, and those are going to be from our first fiber, which in our example is on channel 3. So this is a good time to introduce how to create sensors from our templates. So I guess anyone who's used nLight in the past is pretty comfortable with adding sensors. What may not be familiar is creating sensors from a definition file or a template, and that is this third button down here under the sensor center. So you can see our Micron Optics logo going into the Create button. So I'm going to go ahead and press that control now, and that brings up a dialog box that shows a list of different MST files, which are these sensor definition files that Micron provides for each of the sensors that we manufacture. So if we look down our list, we see some basic groups, OS31XX, OS32, 36, and so on. The XX is there because there are different particular implementations of each sensor, an OS3110 or an OS3120 based upon its attachment method. But those calibration expressions are going to be the same and reference the same template file. You'll also see different permutations here for an OS3100, for example, where it can be compensated by an absolute temperature or a delta T or a relative temperature. And so it's important to know when we're establishing our system and building our sensors what our source of temperature compensation information is going to be. Similarly for the 3200, the OS3600 is our long gauge optical strain sensor that has 2 FPGs built in, one of which is an internal temperature compensation sensor, so that's all contained within a single template file. We have OS4100 or a temperature compensation sensor, as well as 42 and 4300. Those are our absolute temperature sensor expressions, and then an expression for an OS7100 accelerometer as well. So we'll start out very simply, I think, and bring in the OS4100 temperature sensor. And so we'll select that file and click Open. And what that will do is open up this Create OS 4100 sensor window. So we can give it a name. We can name it anything we want. I will call it, very cleverly, OS 4100 WebEx. And you can see a couple of things have automatically been brought in here. First is the model number of that sensor, as well as a description. Here, this is a relative temperature compensation sensor, and it brings in the expression. In the case of the 4100, that's a pretty simple expression, but you'll see in later examples that some of these expressions get complex, so it's a real benefit to have that expression automatically imported. Additionally, it will bring in any constants for the optical sensor expression. There's a graphical paradigm here in the constants that a dark gray background is a constant that's intrinsic to the sensor and does not need to be changed by the user. For certain sensors, such as a strain gauge, which will require the CTE of the substrate, you'll see user editable constants that have, what is it, Dan? I believe it's a white background. Okay, and so if you see a white background, then as a user you're going to need to enter in those specific constants as it pertains to your application, but the dark gray backgrounds are constant for the sensor. So we have the expression, any constants that are required, and of course our expression is going to be a function of the FBG wavelength. And so this Create Sensor pop-up window gives us the option to select that FBG. In our particular case, our OS 4100, that's very funny, put it in the wrong order, I believe is our fifth optical sensor on channel 3, so that would be FBG C5. I may need to verify that's correct here in just a minute. Okay, and so we say okay, and then we have that sensor. Okay, so that is correct. So now we've created our OS 4100 WebEx sensor. It's got units of degrees C, we see here in the second column, and right now it's got a current value. This is a relative temperature value of about 0 degrees C from when we first zeroed the sensor. We also notice that we have a range that goes from -34 to +34 degrees over the current temperature. And
let me add in there, when you create a new sensor using the templates or using the putting it in manually, Nlight will automatically take a snapshot of any of the referenced FBGs or external sensors within that sensor, and it will create reference values for you, which is why our delta T measurement is coming up as 0. It took a snapshot of FBG C3 at its current value and is now using that within the formula. One thing I'd like to point out that I've seen happen to users that are creating their configuration offline is you can create sensors offline when you are not connected to the system. If you do, when Nlight attempts to take a snapshot of your FBG, of course you're not connected to the instrument, so they have no value. What will happen is Nlight will take the center of the FBG bin as the reference value, and then once you do connect to your system, what can happen is you'll see a large value for the measured result. And the reason is that when you created it offline and then hooked up to the system later, you'll need to re-zero your sensors, and that can cause a little bit of confusion when you first connect and see these large values. But just know the reason is when you're creating offline, Nlight doesn't have a way to know what that value is, so it tries its best by using the center of the wavelength bin.
Okay, so now we have established an OS 4100 sensor, and that's going to be our source of temperature compensation for our OS 3100 sensor. So let's go ahead and create a second sensor from template as well. Okay, so back to create from definition, and we are going to select the OS 3100, and then we have to choose between absolute temperature and delta T compensation. We know that our 4100, which is a delta T sensor, is going to be used for compensation, so we'll choose this third template. Okay, so this is the same create OS30 or create sensor pop-up, so I'm going to call this an OS3100. Again, WebEx for our demonstration. We see a description, an externally delta temperature, for example, an OS4100 compensated strain sensor. And now you can see that this expression has become significantly more complex than our previous. So we have a parent expression that shows us two terms here. There's a total strain experienced by the sensor minus the thermal component of strain, this epsilon T0, and that epsilon T0 is a function of the delta temperature seen by the sensor as well as some coefficients. Again, some of these coefficients are going to be intrinsic, inherent to the sensor, such as C1 and C2, and those have our dark gray background. And now as the user, we have to supply two coefficients to nLight, one of which is the CTE, so that's basically going to be the coefficient of thermal expansion of our substrate. What are we measuring? So we'll put a value here of 16. That would be characteristic of the structure that we're measuring. And then also the gauge factor, F sub G. This is going to be identified on the sensor information sheet for your specific optical sensor. It just so happens that most of the OS3600 sensors are very close to 0.89, and so that's what we're going to use in our expression. So now we have two more elements to identify before we complete our sensor creation. Notice under FBG we have the opportunity to filter down between channels before we select our FBG. This is very useful when you have a system with a very large sensor count. Rather than having to scroll through all of your FBGs, we can first focus on channel 3, which is where we know our sensors, our OS3100 sensor is, and that limits our list to only those. And in our case, our OS3100 strain sensor is our third FBG on channel 3, or FBG C3. So we select that FBG, and if you'll notice, that variable has been replaced in the expression, and then we also need to identify a source for our relative temperature. So far in our system, we've only created one temperature sensor, and so that's offered to us here. If we had multiple temperature sensors, we'd be able to choose which one would best represent the temperature changes seen by our OS3600 strain sensor. But here we'll select our OS4100. And now we see that the value of the OS4100 WebEx has been identified as delta T. And now that's going to filter up through these sub-expressions and expressions as we calculate the temperature compensated strain on our OS3600. Okay, so now in our sensor table we have two sensor elements. One, a strain with units of microstrain, and one, a temperature sensor with units of degrees C. And so right now we note that we don't have an effective range. We see these dash marks inside the range. This basically implies that we have not established a large enough wavelength band for that FBG to accommodate both the wavelength shift that it's going to see as a function of operating temperature and the wavelength shift that it's going to see as a function of strain. So when we are creating our optical sensor networks, it's important to remember that our FBGs are going to see wavelength shifts from two factors. One is the measurement quantity for which the sensor has been designed, displacement, acceleration, strain, or whatever it might be. And then also that FBG is going to have wavelength shifts induced just because of changes in operating temperature. And so as we establish spectral bins on this graph on the upper right side of the Sensors tab, we need to make sure that we're provisioning for both those shifts that are going to be seen by changes in ambient temperature, as well as shifts that are going to be seen by the desired measurement quantity, such as strain or temperature.